Young minds, welcome to another session of All Force e-learning program. I am DNR. This is physics session number 63. Now in this session we will talk about the relation between potential difference and electric field intensity. So today's topic is relation between V and E. A very important topic, very useful for many of the entrance examinations. So before going to this, let's have a rewind all the things what we have learned. So I was telling you, charge is a fundamental property. Every charge produces field around it. There are lines of force produced by the charge around the field. Every field has intensity. So the electric field intensity E, it is defined as the force experienced by unit charge. The electric field intensity E, it is force experienced by unit charge, right? So we have derived the formula for the electric field due to many charges. Then later we came to potential. The potential is the electrical state of the body. It determines the direction of flow of charge. Well, electric potential is defined as the amount of work done in moving a unit charge from infinity to the point in the field. Work done to move the charge from infinity to the point in the field. Right, so that is electric potential. Then potential difference. Well, potential difference between 2 points is the work. Potential difference between 2 points is the work done to move the body from the initial point to the final point by Q naught. Well, again, potential due to a point charge. We have found the potential due to many things, many charges. Potential energy, it is the work done in moving a charge from infinity to the point in the field. Potential energy is independent of the path. It depends only on the initial and the final point. Then in the previous video we were talking about equipotential surfaces. So I was telling you, an equipotential surface is the locus of all the points in the charge system, in the field. The locus of all the points in the field where the potential is always same at all the points. The electric potential is constant at all the points. The locus of all the points in the field where the potential is a constant is equipotential surface. Well, at all the points the potential is same. In the sense, the work done, potential difference is zero. So the work done in moving any charge from one point to another point on the equipotential surface is zero. Right? So the work done in moving a charge, any charge from one point to another point is zero. So potential difference between any 2 points on the equipotential surface is always zero. Right? Now, equipotential surface can be a surface of a body, or it is the imaginary surface in a field where the potential is constant. Equipotential surfaces are always perpendicular to the lines of force. At any point the line of force is normal to the equipotential surface, right? Always normal to the equipotential surface, right? And as electric lines of force do not intersect one another, equipotential surface also do not intersect with one another. Never, two surfaces will never intersect, because if two different, this is a plane of one potential, this is a plane of other potential, if they intersect, at the same point it will have two different potentials, which is impossible. Suppose this is a equipotential surface of potential V1, this is another potential of surface V2. So at this common point, at the same point, there must be two different potentials, which is impossible. Right? So therefore, potential, it's not possible like this. So therefore, no two equipotential surfaces will cut each other, intersect each other, right? And equipotential surface for various bodies we have taken. For point charge, it is a family of concentric circles, infinite number. For point charge, it is infinite number of concentric circles. For plane, suppose if uniform field, if I consider a uniform electric field like this, then equipotential surface are parallel planes like this. Parallel planes at any point perpendicular to the electric lines of force. They are parallel planes. Well, in uniform field, they are equidistant. In non-uniform field, the distance differs. If the field is non-uniform, in non-uniform field, the equipotential surface are curved planes. They are curved planes, curved surfaces. Well, not equidistant. The distance differs. Distance between the equipotential surface determine the strength of the field. Suppose if this is a potential V, this is 2V, this is 3V, this is 4V, this is 5V. Well, the potential difference is same between two surfaces, but the distance is different. This small distance corresponds to stronger field. Right here the field is more. Right here the field a bit less, still less, still less. Suppose if I take these points as A, B, C, D, EA greater than EB greater than EC greater than ED. Same potential difference between these two. Potential difference is V, distance is less, field is more, stronger field. Next, field, the direction, in the direction of the electric field always potential decreases. In the direction of the electric field always potential decreases. In the opposite direction potential increases. That is the reason why if a positive charge is taken in the direction of the field, then it loses its potential energy. In the opposite direction it gains its potential energy. An electron moving in the direction of the electric field, an electron, suppose if the electron is moving in the direction of the electric field like this, its potential increases. Opposite direction it decreases. So this way you explain the equipotential surfaces, potential, all these things. Now coming to the relation between electric potential and electric field. Now how do you define or how do you explain the potential and relation between potential and electric field is given like this. Well, let's get the relation between V and E. Now let me consider an electric field like this. An electric field, non-uniform electric field like this. Imagine at a point, let the electric field at this point be E. A tangent drawn to the line of force gives the direction of the electric field. Let it be E. Let there be a charge Q0 at this point, Q0. The force on the charge is EQ0. So suppose I am moving this charge through a small distance, right? Well, let me take it like this. Through a small distance from here to here, this is the initial point A, final point B, initial point, final point, through a small distance dr. Then the small work done in moving the charge from here to here, we know F is equal to E dot dr. According to first year work done, W is equal to F dot S, force into displacement. Then small work done dW is F dot dr. But you know F is EQ, so I can write as EQ. Q0 is the charge that is moved, dot dr like this. So the small work done in moving the charge through a small distance dr at that point where the field is almost same. Let's suppose these two field is almost same. Then dW is E dot dr. Now the total work done to move from one point to another point in the field is integral dW initial to final point. So this I can write as the total work done is EQ0 dot dr from initial point to final point. Right? So therefore the work done dW. But we know the electric potential difference delta V. It is the work done in moving a charge against the field. Delta V is minus dW by Q0. So potential difference between 2 points is the total work done. So it is minus integral EQ0 dot dr by Q0. Well, Q0 cancel. Right, this is initial point to final point. So final potential minus initial potential is minus of initial to final E dot dr. So this is the relation between the potential difference and electric field. So therefore final minus initial, well you can write that this initial point is A, final point is B. So VB minus VA is equal to minus integral of A to B E dot dr like this. Final minus initial point to final point work done. Right, so therefore the potential difference between 2 points, it is E electric field intensity at that point into small dot dr. So this way you can write down the potential difference. In short, suppose if I take this in for small element of charge, for a small elementary distance, then the small potential difference, if I take small work done, so the small work done dW is equal to EQ0 dot dr. Right, this is dot dr. then the small potential difference is minus dW by Q naught. So it's minus E Q naught dot dr by Q naught. Well, dV I can write as minus E dot dr, or E I can represent it as minus dV by dr. So this is the relation between the electric field intensity and electric potential difference. Electric field intensity is the negative of dV by dr. You know, dV by dr, it is the difference in the potential between 2 points, the distance between them. Rate of change of potential with distance. The rate of change of any quantity comparing with distance is called as gradient of the quantity. So it is the potential gradient of the quantity. So the electric field intensity is the negative of the potential gradient. So electric field intensity E is negative minus of the potential gradient of the quantity. E is minus dV by dr. So electric field intensity minus dV by dr. If I cross multiply, so I get dV is E dot dr. dV is E dot dr. Integrating the total potential difference, you can find out. Now these two are the very important relations using which, if the potential equation is given and you are asked to find the electric field, then the electric field intensity is the negative differentiation of the potential. Negative of the potential. Similarly, if electric field equation is given, then you are asked to find the potential difference, then it is the integration of E dot dr there, right? So it is the negative of the potential gradient. Electric field intensity is the negative of the potential gradient, and potential difference is the negative integral, negative line integral of E dot dr, because the electric field is a conservative field, it is independent of the path followed, so it is the line integral of E dot dr. Okay, so this way you can get the relation between the electric field and electric potential there. Okay, right? Now next, let's suppose the potential at a place is given as a simple illustration. A potential at a place is given as V equal to something like 4x square, a previous sentence question actually. Potential V at a place is given as 4x square. Then he is asking you to find out the electric field potential at a point x equal to something like 2. At x equal to 2, then electric field intensity is the negative of minus of the potential gradient. It is the negative of the potential gradient there. So electric field E is equal to minus dV by, well, with respect to x it is dV by dx. Minus dV by dx there. So E is equal to minus of d by dx of the potential whatever that is being given. It's 4x square. So E is equal to minus differentiation minus 4 of d by dx of x square. Well, we have studied in first year that differentiation d by dx of x power n, it is nx power n minus 1. The differentiation is nx power n minus 1. So from this we can write E is equal to minus 4 differentiation of x square. It is 2x power 2 minus 1. X power n, nx power n minus 1. X power 2, it's 2x power 2 minus 1. So E is minus 4 of 2x power 1. So E is minus 8x. Well, x is given as 2. So E is minus 8 into 2. It's minus 16. Well, magnitude is 16. Direction, it is along x-axis. So I cap. So E bar is 16 along minus I cap, negative x-axis. So this way you can find out the electric field there. If you consider the thing there, potential with distance, it is V proportional to x square. As x increases, potential is increasing. As when x is 0, potential is 0, x0, potential 0, x1, potential is 4, x2, potential is 16. So as x increases, potential is increasing. But we know potential always decreases in the direction of the field. As x is increasing, potential increases. As x becomes negative, right, its potential decreases. So therefore the electric field is in the negative x direction. That is the reason it is minus I. You know, in the direction of the field, potential decreases. In the opposite direction, it increases. So, you know, as x is increasing, x0, potential 0, x1, potential 4, x2, potential 16. As x increases, potential is increasing. Right? Actually, potential decreases in the direction of the field. Potential increase in the opposite direction. So, this is opposite direction of the field. So, the actual direction of the field is minus. So, this way you can find out the field there. Similarly, suppose if the same question is given, if the same thing is given in the other terms, as suppose the electric field is given as an equation, the electric field at a place varies as E is equal to some Ax minus B. Then he is asking to find the potential difference between 2 points, or potential at a point considering the initial point at infinity, and the potential at infinity is 0. Then the electric field is Ax minus B. So we know potential difference between 2 points, V final minus V initial, V final minus V initial is integral initial to final E dot dx. Well, this is with respect to x, so it is E dot dx. So V final minus V initial is minus integral of initial from infinity. We are taking the body from infinity, initial point, initial to final, initial point to final point E. It's Ax minus B into dx. Well, so this is also along the x direction only. So therefore dx is also x direction. Dot product E dx both are in same direction. So you can simply write as E dx from initial to final. So therefore V final minus V initial is minus initial point to final point integration Ax minus B dx. Well, integrating each term, you know, integral of x power 1, x power n dx, we know it is x power n plus 1 by n plus 1. So taking the integration, V final minus V initial is integral of initial to final Ax dx. So it is Ax of dx minus integral initial to final B dx. Well, perform the integration and substituting the term initial. Let the initial point be x1, y1 and the final point be x2, y2. Then perform the integration and substituting the thing. You can find out the potential difference. So this way, when electric field is given, you have to perform the integration. When potential is given, you have to perform the differentiation to find the electric field like this. Sometimes the question is also asked like this, you know, potential difference dV is equal to minus E dr, E dot dr. Now, potential difference between 2 points, he says, suppose electric field is given as E vector, it is something like A I cap plus B j cap plus C k cap, C k cap. Now, what is the potential difference between the point x1, y1, z1 and another point x2, y2 and z2? This time in vector form. So, initial point A, final point B, potential difference between these two. So, potential difference between these two dV. So, it's V final minus V initial is minus E bar dot the displacement vector AB bar. Right, displacement vector AB bar. So, therefore, E bar dot AB bar. So, VB minus VA, it's equal to electric field. Well, AB bar you can write as from vectors we know. It is x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Well, substituting you get minus ai plus bj plus ck is the electric field dot x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Now applying the dot product, you know, first year dot product, if a1 b1 c1 a2 b2 c2 are two vectors, a1 a2 plus b1 b2 plus cn c2, perform the dot product, you will get the answer. This is another way of finding it. Sometimes he will give you the graph between the potential and the graphical variation of v with respect to x is given like this. For example, well, this value is something like v naught. This is x naught, this is 3x naught, let us say 4x naught, something like that. Now he is asking you to find the potential at some point x equal to x1, somewhere here. Then we know dv is equal to minus e dx, or e is equal to minus dv by dx. It is the negative of dv by dx, slope of the graph. He is asking you to find the electric field at a point. Potential displacement graph he has given. He is asking you to find the electric field at any point there. So E is minus dv by dx. It is minus of dv by dx. It is the slope of the graph at whatever point x equal to x1. Slope, you have to find the slope. Well, what is slope? Tan theta. So E is equal to negative of tan theta of the value. Suppose if I consider this as theta, in this right angle triangle tan theta, it is opposite by adjacent side. Well, from this tan theta I will get it as opposite is V0 and the adjacent is x0. Well, substituting E is equal to minus of tan theta, it's V0 by x0. So the electric field is the negative of the potential gradient, minus of the potential. So when a graph is given, you have to find it by slope. You see, there are different, I have given you different methods now. How to find the potential when field is given or field when potential is given. When the equation for potential is given, potential is expressed as an equation, ax square plus bx plus c, then you have to find the electric field by differentiating V. Suppose if E is given as ax minus b, then potential we have to find by the integration of E dot dx. If vector form, E is given in vector and displacement in vector, then the potential is minus E dot r. When a graph is drawn between potential and distance, then the electric field is minus of the slope of the graph. It is minus tan theta. So this way, for different variations, you have to find for different examples, whatever he gives and how to find the other. Now these are the methods to find the things there. Okay, right? This way. Okay. Now, consider two potential equipotential surfaces where the potential is V and the potential of this one is V plus some dV. Let a charge Q0 be moved from the point A, x comma y comma z to a point B. Yes, these two surfaces are very close, small distance, where this is x plus dx, comma y plus dy, comma z plus dx. So the charge Q0 is moved from here to here like this. Then the small work done in moving the charge from here to here is f dot dr. Well, dr displacement vector, dr bar is equal to x2 minus x1i. You know, x2 minus x1i, y2 minus y1j, z2 minus z1k. So it is dx I cap plus dy j cap plus dz k cap. Let the electric field between these two be some E. Then we know the force F is equal to EQ0. Then the small work done dW I can write as minus EQ0 dot dr bar. So the small work done is minus E, the work done by Q0 is minus, it's E dot dr bar. E dot dr bar. So therefore we know this dW by Q0 work done. So negative of minus dW by Q0, this is minus E dot dr. The negative of the work done per unit charge is dV. It's minus E dot dr. So E can be written as, now the potential difference. Now the total potential difference between these 2 points I can write as, potential difference between these 2 points I can write as dou V by dou x into dx. Well, the potential due to x parameter, because the electric field in 3 dimension, this is Ex, Ey and Ez. There are 3 dimensions. So dou V by dou x into dx, dou V by dou y into dy plus dou V by dou z into dz. Splitting this into vector form, so dv I can write as dou v by dou x I cap plus dou v by dou y j cap plus dou v by dou z k cap dot dx dy dz I can write as dx I cap plus dy j cap plus dz k cap. Well, so potential difference is equal to the total potential difference between these 2 points. Actually, potential dv, let me multiply dx and dx, dy dy, because the potential variation is along x, the electric field components along x, y, z. So dou v by dou x, splitting into vector form, this is dot product, according to dot product a1i plus b1j plus c1k a2i b2j c2k dot product a1 a2 a1 a2 plus b1 b2 plus c1 c2. So from this dv I can write as minus of this dx I cap dy j cap dz k cap is dr bar. So therefore dv is equal to minus of dou v by dou x I cap plus dou v by dou y j cap plus dou v by dou z k cap dot dr bar. Now comparing these both, this is minus negative of dv by dx is dv. So comparing these both, potential difference can be written as minus e bar dot d bar minus this dot dr bar. So this is dr bar. So comparing, I get electric field E is equal to minus of potential difference, it is minus dou v by dou x I cap minus dou v by dou y j cap and dou v by dou z k cap. So this is the electric field. It is the negative of the gradient of potential. You can write in short, E is minus delta. So potential difference, gradient, the gradient is denoted like this way, E is minus delta V. So in vector form you can represent in partial differentiation also like this. So Ex, so that is actually electric field along x direction, it's dou v by dou x minus electric field along y direction I cap along y direction minus dou v by dou y j cap, electric field along z direction minus dou v by dou z k cap, like this. You can represent the components in this manner. So the electric field is the negative of the gradient of electric potential. You can write in vector form like this. So this way the potential relation between potential and electric field